Hello everyone, my name is Xingjian Diao from Dartmouth College. I'm excited to present my work, which titled Temporal Working Memory, Query-Guided Segment Refinement for Enhanced Multimodal Understanding. This work is part of our efforts to rethink how multimodal foundation models handle video and audio inputs, especially in terms of efficiency and relevance. We will walk you through the key ideas, including how we use memory-inspired mechanisms to refine temporal segments. So let's start with what challenges this work was designed to solve. Our motivation stems from a critical observation about current multimodal foundation models. First, they lack the ability to extract query-relevant information. Instead of focusing on what's important for a given task, they process the entire input sequence, regardless of its relevance. This leads to inefficient and noisy representation learning. Second, these models are weak at temporal reasoning. They struggle to handle both short-term dynamic changes and long-term dependencies in multimodal data. This greatly limits their ability to understand events that evolve over time. Humans, on the other hand, are good at selectively attending to information that matters, guided by a goal or question. It's the idea of a task-driven, selective memory-inspired solution, temporal working memory. Imagine watching a 1-minute video and to answer the following question: what is the first on the instrument? The video might show a person entering a room, picking up objects, background music, and other people speaking, but only a small part is actually relevant to answering that question. However, most of multimodal foundation models process all of this input equally, from start to finish. They lack of the ability to filter based on the task. So the question is, can multimodal foundation models selectively return only query-related segments, just like human working memory doing? Here's our answer to the key question: temporal working memory. The process begins with a language query, which could be a natural question or task instruction. The query is encoded and then used to guide a multimodal segment search. They pinpoint the video frames and audio segments which are most relevant to the task. These selected segments are stored and refreshed in a working memory buffer, which mimics how human working memory does. Finally, the refined inputs are passed into standard multimodal architectures for downstream tasks, including question answering and video captioning. The next few slides will go through each steps in more detail. Our video segment selection module consists of two main steps. First, we assign each frame a similarity score, combining how visually distinct it is and how relevant it is to the query. This is controlled by adaptive weights depending on the task and video length. Then we perform iterative selection. We choose the highest score frame as a center point and uniformly select keyframes around it in a fixed window. The memory buffer is updated only with the non-duplicate frames, and repeat this progress until convergence. Our audio memory module is designed to selectively return segments that are both semantically relevant and temporally informative based on visual content. Rather than using the language query directly, we use the visual embeddings as the retrieval anchor to guide audio segment selection. This reflects to the idea that what you see often informs what you hear. To synchronize audio and visual information, we optimize their embedding alignment using unfounded E-loss. To support temporal reasoning, we apply two complementary attention mechanisms: inter-segment attention module for global structure across audio clips, and intra-segment attention to capture local audio patterns within segments. We evaluate our proposed temporal working memory across three representative tasks: audio-visual question answering, video captioning, and video text retrieval on 9 state-of-art multimodal foundation models. We test our proposed temporal working memory on Music AVQA version 2 for audio-visual question answering tasks. Across all baselines, integrating temporal working memory consistently improves performance. This shows that temporal working memory helps multimodal foundation models focus on relevant segments, which is important for fine-grained multimodal reasoning. We test video captioning on MSR-VTT dataset following the standard metrics. Our temporal working memory improved multimodal foundation models' performance by focusing on key video content. We evaluate temporal working memory for video text retrieval tasks on the CMD dataset using standard retrieval at key metrics. The mechanism significantly improved retrieval performance across all baselines, enhancing cross-modal alignment over extended temporal sequences. We already see constant improvement from temporal working memory across all three tasks. So let's see how it works. In our video caption example, the working memory selects just 8 frames from hundreds of frames, but already capturing all key actions like chopping and mixing. This leads to cleaner and more accurate captions, while also saving computation. To conclude, multimodal foundation models often struggle with dynamic video-audio language input due to the limited capacity and inefficient memory usage. We introduce temporal working memory, which selectively return relevant segments, models multi-scale dependency, and extract query-related information. This mechanism consistently improves 9 state-of-the-art models across 3 challenging tasks. Thank you for your attention. For more details, please feel free to check our paper.